Hi, welcome again in Operations Management tutorial video. Today is our 10th session and this is the last session actually. And today we're gonna do some exercises related to chapter 17 and it's about maintenance and reliability decision. But first, what is maintenance and reliability? So basically maintenance is the activities involved in keeping a system's equipment in working order, while reliability is the probability that a machine part or product will function properly for a specified time under stated conditions. And each of them has its own tactics. It's like for reliability, there are two tactics. We could improve individual components for reliability, or we could provide redundancy. While for maintenance, we could implement or improve preventive maintenance, or we could increase repair capabilities or speed. So those are the tactics for each of them. And now let's do the problem. We have 6 problems today, and let's start with the first one. Okay, here we have Robert Clausen Manufacturing is a medical equipment manufacturer, and they subjected 100 heart pacemakers to 5,000 hours of testing. Halfway through the testing, 5 pacemakers failed. And what was the failure rate in terms of the following? Percentage of failures, number of failures per unit hour, and number of failures per unit year, and then MTBF or mean time between failures at this point in the testing. And the last one is, if 1,100 people receive pacemakers implants, how many units can we expect to fail during the following year? Okay, so the info given is the number of failures. Okay, the number of failures is 5 pacemakers, and then number of unit tested is 100, right? Subjected 100 heart pacemakers, and then the total time is 500,000 hours. Okay, we get it by multiply the 1,000 hours of testing multiplied with the 100 heart pacemakers, so the total is 500,000 hours. Okay, let's start with point A. How many is the percentage of failures? So the percentage of failures, we could refer to this formula. First one is failure in the percent of failures among the total number of product tested. We could use this formula, okay? The number of failures divided with the number of unit tested and then multiplied with 100%. We know that the number of failures is 5 pacemakers, and then the total of pacemakers being tested is 100 units. So the percentage of failures is this one, okay? 5 divided with 100, and then we multiplied with 100%. And we get 5%. So that's the percentage of failures. And then move to point B, number of failures per unit hour, and number of failures per unit year. So before we count for this failure per unit hour, we have to know how long is the total time, and then the non-operating time, and also the number of unit hours of operating time. We know that the total time is 500,000 hours, right? And then there's also non-operating time, because we know that there are 5 pacemakers failed halfway through the testing. So it means that there is the non-operating time because the testing has failed. And how long is the machine is failed to operate or to test those 5 pacemakers? We know that the total time is 5,000, right? Or maybe we know that per test it takes 5,000 hours, while there are 5 pacemakers that failed. So we know that the non-operating time is the halfway through the testing, the halfway. So it's the half of 5,000 hours. And it means that per or one pacemaker, it only took 2,500 hours, right? And the rest of it is stopped. The machine stopped because the testing is failed. So we get it, the non-operating time. We get it by multiplying the number of failures, which is 5 pacemakers, and then we have to multiply it with 2,500 hours, okay? Because the testing has failed halfway through the process. Okay, now for number of units hours of operating time, we get it by decrease the total time with the non-operating time. So this is the number of unit hours of operating time. So this is how long as the machine is in process. And now we could calculate for the number of failures per unit hour. Okay, for this one, we could use this formula, okay, number of failures divided with number of unit hours of operating time. We know that the number of failures is 5 pacemakers, and then the number of unit hours of operating time is this one. So we have to divide them. So 5 divided with this number, and we get this number 0.0000103 failure per unit hour. So this is the number of failures per unit hour. And the second one is the number of failures per unit year. So how do we get it? We could get it by multiplying this number, okay, the number of failure per unit hour, and then we assume that in a year there are 365 days, and in a day we have 24 hours, so we have to multiply the number of failure per unit hour with 365 days and multiplied it also with 24 hours, and we get the number of failures per unit year, which is 0.09 failure per unit year. Okay, so that's for point B. For point C, how much is the MTBF or mean time between failures at this point in the testing? So to find the MTBF, or MTBF means the expected time between in a repair and the next failure of a component, machine, process, or product. And we find the MTBF with this formula, okay, 1 divided with the number of failure. Okay, we already counted for the number of failures. There are number of failures per unit hour and also per unit year. But in this case, to find the MTBF, we use the number of failures per unit hour instead. So it becomes 1 divided with this number, not this number, okay? So the mean time between failure is 79,500 hours. And please note that the MTBF is the expected time between a repair and the next failure. Either it's component, machine, process or product. And then the last point is point D. If there are 1,100 people receive pacemaker implants, how many units can we expect to fail during the following year? Okay, so we're being asked about number of expected failures, and we could find this number by multiplying the number of failures per unit year, which is this number 0.09, with the number of people that receive pacemaker implants, which is 1,100 people. So the total is 98.83 failure. So this is the expected number of failures if there are 1,100 people receive pacemaker implants during the following year. Okay, so that's for problem 1. Okay, next to the second problem. Here we have a reliability problem. A company has the following production process system. As you can see here, there are 4 machine or components, so each box represent a different or specific job, and then we have to calculate the reliability of the system. And then suppose that R1 fell to 0.56, what will happen to the overall process and what should be done to improve the reliability of this process. So before we do the answer, basically a system is composed of a series of individual interrelated components, and each of them performing a specific job. Okay, so as you can see here, as I said before, there are R1, R2, R3, and R4. Each of them represents a different job. And as the number of components in a series increase, the reliability of the whole system declines very quickly. So to find the reliability for a system with series form, we have to multiply each reliability of the components. Okay, where R1 or R2, R3 is the reliability of component, each of them. But you see that for R2 and R3, the form is not a series, right? It's a parallel. So basically R3 is the redundancy for R2 or the backup for R2. And before we calculate the reliability for the overall system, we have to find the reliability of these two. So we have combined 2 of them. Okay, so this is the picture of this system. For point A, before we find the reliability for the overall system, as I said, we have to find the reliability for these two. Okay, for R2 and R3, we have to combine, and we could find the reliability for the parallel form by using this formula. Okay, because it's redundancy, as I said before, so we have to use this formula to find the reliability for the parallel. So you have to add the probability that first component works, and in this case the first component is R2, and then add it with the probability that backup works, which is the R3, and the probability the backup, we have to multiply it with the probability that first fails. So it becomes like this. You could use this one or this one, but I prefer to explain this instead. Following this form of formula, probability that first component works is R2, which is 0.85, right? And then plus the probability that backup works, which is 0.852. But we have to multiply the reliability for R3 with the probability that first fails. As I said, the first is the R2, and the reliability for R2 is 0.85. So the probability for this one fails is 1 minus 0.85. So it's 0.1. 0.15, right? So the probability that first fails, you just have to decrease 1 with the reliability of the first component. So we have to add 0.85 plus this calculation, which is 0.1275, and the reliability for this parallel form. Finally, we have this number 0.9775. And after we calculate for this parallel form, finally we get this series for the system. Okay, and finally now we could count for the reliability for the overall system. Just like this one, you have to multiply each reliability of the components if the form of the system is already in series form, like this one. If it's still have this kind of form in parallel, then you have to find the reliability for this form first. Okay, that's the note. And now we could multiply this number. For R1 is 0.9, and for the combined of, we have combined the R2 and R3, and the reliability is this one, and multiplied with this one, 0.9, and then we have this number as the reliability for the overall system. So that's the answer for point A. And for point B, suppose that R1 fell to 0.56. What will happen to the overall process, and what should be done to improve the reliability of this process? So if R1 fell to this number, okay, before this number we have 0.9, right? And it decreased to 0.56. Then you just have to recalculate the reliability for the overall system. You just have to change the number of this one. Before it fell, it's 0.9, and now it becomes 0.56. Then you have to divide with the rest of them. It still remain the same. And finally, we have the new reliability for the overall system, and it's actually decreasing, right? Before it fell to this number, before the R1 fell to 0.56, we have 0.79 blah 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 as our reliability for the system. And now we have 0.49266 when the R1 fell. So the reliability of overall system is decreased. And what should be done? We have to install a backup machine or redundancy for machine 1. So basically the redundancy, it would become like this. So the R1 should have the redundancy or in form of parallel. So that's the solution for problem 2, and we move to problem 3. Okay, in problem 3, actually it's still the same. With problem 2, we have to find the reliability for the overall system, but this one is just a bit more complex than the previous system 1 in problem 2. As you could see here, there are so many parallel form for the components, like this one and this one, also this one, and at the end it becomes the parallel 2 for the above line, this one, and the below line, this one. Okay, so we have to do it one by one. As I said before, we have to work on the smallest form first, like this one. As you could see, we have 0.8. It's the first component, and the redundancy is this one, 0.95. And we have to find the reliability for this 2 first. So we could find the reliability for the combine of these 2 with this one, 0.85. And also this one, we have to find the reliability for these 2 first, and then we multiply the result of combining these two with this one, multiply, and then we have to find the reliability for this form of parallel, 0.78, 0.95, and the result of these three, and also this one, 0.9. We have to find the reliability of these two. This is the redundancy, 0.85, and finally we have to multiply, because next it will become series, so we have to multiply this section with this one, and then they become 1, and this one will be multiplied with 0.77, and they become, because they are series, and they become 1, and the last one we have to multiply this part with this part. Okay, so let's start with this figure. Okay, so actually I already marked which one we should have done first. So okay, for this one, R8 and R9. Okay, sorry, for this picture there's not a name for each component, so I add it here in the picture that I made. So we have to work on this, and then this one and this one first, because they are the smallest part of the system. Okay, start with this one. I call it with RT1, or the total of the reliability of this parallel series or parallel form. As I said before, you could use this formula, okay, 17.5, or you could use this kind of formula, 1 minus 1, and then minus the first component, the probability of the first component, and then you have to multiply it with 1 minus the probability of the redundancy or the backup, and then we find that the result is 0.975 for this one after we combine these two for RT1, and then for RT2, which is this one, we combine R10 with R11, so R11 is the redundancy for R10, and the reliability for these two is 1 minus 1 minus the probability of the first component, and then multiplied with 1 minus 0.85, and we have 0.985 for this form of parallel. And then the third one is this one in the above. The R2 is the redundancy for R1, so it became like this, 1 minus 1 minus the probability of the first component, and then multiplied with 1 minus the probability of the backup, and we get 0.99. That's for the most in of the system. And then we have to find this form. Okay, it's a bit dark, so I guess you have to increase the brightness on your screen. Okay, we're done doing this 3RT, and now move like this one. After we combine those components, like R8 with R9, and then R10 with R11, R1 with R2, and the system, the form of the system become like this. Okay, it's the R3 that we count above. It's the RT1, and this is the RT2 after we combine the parallel form. And now we still have work on this form because it's still in a parallel form. So we have to combine them and find the reliability for these two using like this one formula. And because this one is in a form of series, so we have to just simply multiply both of them. And I named it as RT4 for this one, this series, and parallel is RT5. And for RT4, because it's series, so we just have to multiply 0.85 with 0.975 like this one, and we get 0.83 for RT4. Okay, for this one they become 1 and the reliability becomes 0.83. And then for the RT5, this one, the parallel one, as usual you have to use this kind of formula, 1 minus the probability of the first component, and in this case is RT3 because it's the above, it's in the above, and then multiplied with 1 minus 0.85 because it's the probability of the redundancy, and we get 0.9985. So for this one, the reliability become this number, and the reliability for this one, R7 and RT1, is this one, 0.83. And finally, we have the new form of the system like this one because we already combine this R7 and RT1, also RT3 with R3. Okay, after we combine, we get that the RT5 is 0.9985, and the RT7 is the RT4 it is this one, as we count before. And finally, we still have this kind of form in the system. We have the series form, this one, RT5 with R4, and we have the parallel form for R5, R6, and RT4. So we have to work on them. We have to combine RT5 with R4, and since it's series, so we have to just multiply the reliability of them. So it becomes for RT1, I called the combination of RT5 and R4 is RT6. So it becomes 0.9985 times 0.77, and it becomes 0.768845. So the RT6, or the combination of RT5 and R4, is this number. And for this one, okay, the combination of R5, R6, and RT4, we have to use the formula for redundancy because they are in the form of parallel, and it becomes 1 minus 0.78 because that's the probability of the first component, which is R5, and then we have multiplied it with the redundancy, probability of the redundancy, which is R6, 0.95, and also multiplied with the second redundancy, which is RT4, with the probability of 0.85, and finally we have 0.9981 for the reliability of these three, or we called it as RT7. Okay, so we finally combined RT5 with R4, and then they become 1, and then these three also become 1. So the system become like this. The form of the system become like this, right? This is the RT6 that we count here, and then this is the RT7 that we counted here, and the system become like this. And as you could see here, we still have two kind of forms. This is parallel and this is series. So we have to work on this first, on series first. RT7 with RT2, we have to combine two of them. And since it's series, we have to just multiply the reliability of each of them. And we called it as RT8, the combination of those two. And finally, we have 0.98 31285 for the combination of RT7 and RT2. And finally, the final form of the system is in parallel form, right? The components left is RT6 and RT8 with each of their probability, and since it's in parallel form, so to find the reliability of the system, we have to use the formula of redundancy to find the reliability. Okay, we use this 1 minus the probability of the first component, which is RT6, the reliability of RT6, and then minus 1 minus 1 this one minus 1 minus the probability of the backup, which is RT8, right? And finally we have 0.996 as the final reliability for the overall system. Okay, so that's the solution for the third problem. So the point is you have to look at the system first, and you have to find which one is the most in the system, and you have to work on it first, and you have to notice what kind of form they have in the system, either it's series or parallel, so you could decide what formula you have to use to find the reliability. Okay, so that's all for problem 3, and next we move to problem 4.